This is the video going over the multiple choice review for chapter 9. Okay, so number 1, they give you a bunch of information. It's a 2-sample situation because people were randomly assigned to a drug or a placebo. They did talk about p hat c, so that's the combined proportion, combining the 2 samples together because we want to treat the situation like the whole is true, which means we want to treat it like the proportions are the same. And all we have as far as real data is a sample proportion, so we need to combine them together in a way that creates kind of a single combined proportion that we can use for both. Okay, anyway, here is the formula. You're really just adding your numerators on top of your individual proportions and adding your denominators on bottom. You get a new proportion and a new number. So 0.75 is our p hat c. Now we just go through each, you could just go do all of the conditions separately and then go look at the answers, or just kind of look through the answers. The first one's about the random assignment, and they did say it was randomly assigned, so that is okay. So therefore, that's not the answer. Then they talk about the 10% one. The study was too large compared to the size of the population. So if you think, okay, our sample size for each group was 250. So 250 is 10% of what? So 250 times 10 is 2,500. So as long as our population is bigger than that, we're okay. If our population is bigger than 2,500, then our sample size of 250 is less than 10% of that. And there's more than 2,500 people that have arthritis. Our population of people with arthritis is much bigger than that. So that's not our answer. That condition is okay. And then we're going to check the large counts. We check it with p hat c, 0.75, and we check it with 1 minus p hat c, 0.25. Either way, you get numbers that are bigger than 10. So that condition is okay, so that makes E the answer. All 3 conditions have been checked. Okay, for number 2, it is about picking out the ho and the ha for the situation. They say that a seed company claims that the germination rate for their seeds is 90%. So that's your null value. That is the claim that we are testing out. If nothing interesting is happening here, what this company says is true. The germination rate is 90%. The 80% is your p hat because that came from your random sample of seeds. And your ho and ha, your hypotheses, are guesses about the population, not about a sample. So we always need to be talking about our population value, our null value inside the ho and the ha. And if you were to do the whole process with this, that 80% would come into play as you start calculating things. But just writing the ho and the ha, it's just the null value. It's just p. So it's 0.9. So that narrows it down to answers C, D, and E. And then you need to look at the direction of the ha. So the ha is that we're interested in it being less than 90%. So less than 90%. So you're good there. Answer is C. For number 3, it's picking out which procedure it is. Now, on this test, it's going to be all proportions, because that's all we've done. And it's going to be all significance tests. No confidence intervals. That's the last chapter. So on this test, it's a significance test for proportions. The question is it 1 sample or 2 sample? In this case, it's 2 sample because they have a sample out of supermarket X and they have a sample out of supermarket Y. You're comparing to each other. So we've narrowed it down to A and B. And then they wrote it out a little differently than we have been doing in class. We've been writing kind of a shorthand version. So a 2-sample Z test, we've been saying for P1 minus P2. And that is just a difference. It's a subtraction problem in population proportions. Notice it's P and not P hat. So we are trying to guess a difference in the population, not in the sample. Because the sample we already have. Our hypothesis is about the population. So that makes it B. Okay, number 4. They didn't give us any context. It's pretty general with the general notation. They say, what's the purpose of a 1-sample Z test? Like this whole chapter, what is the purpose of these procedures we're doing? Well, A, B, and C all refer to chapter 8 stuff. They all refer to confidence interval things. That's when you're trying to use p hat to estimate p. Margin of error is part of that calculation. The purpose of confidence intervals, chapter 8, is all about estimating a number in the population, actually getting like a number answer, and then you put wiggle room around it and all that stuff. This chapter was about a claim has already been made. There's already a hypothesis out there, and we are testing that hypothesis to see if we agree with it or not. Do we have evidence to move away from that hypothesis, or do we not? Okay, so it's not A, B, and C. That's all chapter 8 stuff. So now we say to estimate the probability of observing a value as extreme as p hat given p. So keep in mind, all our pictures are always assuming the HO is true. So our sampling distribution is centered around p, the number in our HO, our null value. And we're interested in, okay, we end up with a p hat, some sample proportion, and we want to know how extreme it is. So the whole point of a p-value is to find the probability of landing in that shaded region. And that number is a way to quantify, is p hat really extreme compared to p? Is what we got in our sample really extreme compared to what we expected to get based on the null hypothesis claim? So given p is referring to, we assume the HO is true. So how extreme is the sample, assuming the HO is true? Okay, 5. Got a bunch of information here, and we're just practicing the conclusion part of the SPDC part. Okay, so in this case, they gave us a p-value of 0.37. They gave us an alpha of 0.1, and 0.37 is bigger than 0.1. So our p-value is too big. Our p-value is not low, so we do not reject the HO. There is not convincing evidence of the HA, which in this case is that they're not equal. So you just got to go find the phrase that says that, and that would be D. P-value is greater than alpha, so we're not rejecting the HO. There is not convincing evidence that they're different routes, which is referring to the HA. Okay. 6. Similar to a previous problem, we need to calculate our individual p hats and then turn that into a combined p hat. Again, add your numerators on top, add your denominators on bottom, and you get a new combined proportion that we're going to use in all of our calculations, in our large count calculation and in our standard deviation calculation. So let's just go through our options here. So they did state that they're random samples, so it's not A. So it's about the conditions here. This one, okay, this is just a good heads up. They said a certain town with a large number of residents. They are telling you that for a reason. They're telling you that it's a large number of residents for a reason, that you can assume the population of the town is large enough to make all our conditions okay. I wish on these problems they gave you a specific number to kind of quantify what large means, but I'm just telling you when the AP people write it this way, that's what they mean. They're telling you it's large on purpose so that you know that your 10% condition is okay. Your population is sufficiently large. Okay, so then we do our large counts calculations using our combined p hat, and both of them are okay. So everything is good. All conditions have been met. Okay, number 7. So a big thing to keep in mind, when you have a 2-sample situation, your HO is always P1 equals P2. And if it's a 1-sample, you at least know that it's going to be P equals something. Like the HO should always be an equals situation. So before I even looked at the problem, I knew I could eliminate B and E because the HO should always just be a straight equals situation. And when it's 2-sample, it's specifically P1 equals P2. Okay, and then you look back at the phrasing, and they said whether their approval ratings had changed. So that doesn't imply a direction. They're not saying that our approvals get better or worse. They're just saying changed. Could be either way. So that gives you a not equal to situation. Okay, number 8, I realized once I started making the key that it is using something that we did not get a chance to talk about. There's some stuff at the end of the chapter that we didn't get to, and we just won't have time. So don't do number 8. It won't make sense to you. Sorry. And I replaced number 8 with that extra problem on the other worksheet, so you still get the practice in of that concept in a way that matches what we did in class. Okay, number 9. So similar to a previous problem, they gave us a p-value, which was bigger than 0.05. So p is not low, so we do not reject the ho. There is not evidence of the ha. So just go through and find the one that matches that. Not rejected. There's not convincing evidence. Okay, great. So now I'm going to flip over to the other problem that was on the other PDF that was replacing the number 8. So this is now on a new document, but it's that same concept as number 8. But like I said, it matches what we did in class. So this is a 2 sample situation, and it gets a little bit tricky because you have to keep track of which way it's subtracting in order to be able to get a number to graph on your little normal distribution. Okay, so they said to do old minus new. So that's worth, hang on. I have to get it ready to annotate. Okay, they said old minus new. So we're going to keep track of it as old minus new. Okay. And I'm calling 1 old and 2 new. Okay, so then I wrote out my ho and my ha. I knew it's always P1 equals P2. And they said the alternative hypothesis being that the proportion of defective parts made on the old assembly line is greater than the new. So alternative hypothesis is old greater than new. And old is 1. So old greater than new. And then if you wanted to turn that into something compared to 0, if you subtract P2 from both sides, you get P1 minus P2 is greater than 0. A different way to write your ha. Okay, so all that's kind of figured out. So now we have our normal distribution here. We know that the null value is 0 because if the ho is true, our 2 proportions are equal. So the difference between them is 0. There is no difference, 0 difference between them. And our P1 hat minus P2 hat, our sample difference was 0.06, a positive number. So that's above 0. You could also, anyway, so I have something else to say, but I'll say it at the end. So anyway, so here's your graph. And you're interested in it, I guess I will say it now. If you think of it as P1 minus P2 greater than 0 is also a different way to say, hey, our shading is up on the upper side, the right side. Okay, so let's go to our answers. You know A and B are not right because we always assume the ho is true until proven otherwise. And remember that our ho is at P1 equals P2. So we should be assuming the if there's no difference, that narrows it down to C, D, and E. We know it's not A and B because we're assuming the ho is true in the beginning. And then the probability of observing a difference of at least 0.006, this is 0.006, is 0.018. So it comes down to the shading of the picture. Let me get even smaller here. So if they say equal to 0.006, let me get a different color. That's referring to right here, exactly 0.006, but that's missing all the rest of the shading. So part C is only doing the red line there. It's missing all the rest of the shading. That's why it's wrong. D is saying at least 0.006. So that is that point and everything above. That's the shading we want. E is saying at most 0.006. So that would be saying, let me get a different color again. That would be saying at most 0.006 is everything below it. And that's not what we want. So the answer is D. Okay, that is it.